In this video, we're going to talk about solution formation. So the nature or the polarity of the composition of the solute and the solvent will determine whether a substance will dissolve at all, and if so, how much it will dissolve. There's a saying called like dissolves like. It means that a polar solvent will dissolve in polar solutes, but they won't dissolve in nonpolar solutes. A nonpolar solvent will only dissolve in nonpolar solutes. So if you want to dissolve something that's polar, you need to dissolve it in something that's polar. Or if you wanted to dissolve something that's nonpolar, you need to dissolve it in something that's nonpolar. You can't reverse the polarities. It won't work. It won't dissolve. So there's factors that determine the rate of solution formation. One is stirring. A fancy word for that is called agitation. It just means you're stirring up the solution. You know, if you stir a Kool-Aid or an iced tea mixture, it will dissolve faster. The surface area of the dissolving particles can also affect solution formation. So if it has a higher surface area, it will dissolve faster. If you have a big chunk of iced tea mix, it won't dissolve in water as fast as powdered iced tea mix would. And the third is temperature. These things will usually increase the amount that will dissolve. If you stir or you have a more surface area or you have a hotter solution, you will not only make the solution faster, but you can probably make more of the dissolved solution. All three of these things work because they increase contact with the reactants. If you stir something, you're bringing fresh water, fresh solvent in contact with the solute in order to create a solution faster. If you have a higher surface area, you have more area for the solvent to touch the solute and to dissolve it. And if you have hotter temperatures, you have higher kinetic energy, and the solvent is moving faster and coming in contact and colliding with the solute. So all these things are going to increase rate of solution formation. Sometimes this is different for solids versus gases. So solids tend to dissolve best when they're heated, stirred, and crushed into smaller particles like we just talked about. Gases, however, are slightly different. Gases tend to dissolve best when the solution is cold and when it is under high pressure. Think about soda. Soda is a solution of water and carbon dioxide. That's what makes it bubbly. But the carbon dioxide doesn't get into the water until it is under high pressure. You have to pressurize it. That's why when you open the cap of a soda bottle, you hear that fizzing sound. That's the pressure coming out. Also, we know soda works best when it's cold. If you leave your soda out on a hot day, it loses its carbonation. All the carbon dioxide comes out of solution faster. So what does that have to do with this picture here? So some people might look at this picture and say, oh, look at that awful pollution. Those smokestacks are polluting the air. And it's actually not polluting the air at all. That's water vapor coming out of those cooling towers. This is a nuclear power plant, and the nuclear reaction's happening underground, and that gray tower you see there with the smoke coming out of the top of it, that's actually not smoke. That's just water vapor. It's hot water cooling down before it's released back into the stream. However, this still is a form of pollution. This is called thermal pollution, because when the water is released out of those cooling towers back into this river or stream, it is slightly warmer than usual. And all of the gases that are naturally dissolved in this fresh water, gases that plants need, like aquatic plants need carbon dioxide, or gases like oxygen that the animals need to breathe, it is not dissolved as good in the water. So they have lower gas content, and you get these dead zones around these power plants. Despite the fact the water is very clean, still nothing can live there because it's lost all of the gases out of solution in the surrounding waters. So next thing we're going to look at is how we can decide how much solute will dissolve. And that is going to be table T. So, table G. Table G is the solubility curves at standard pressure. So I'm going to teach you how to use this table, but before we do, we need to talk about a couple of vocab words first. The first is solubility. This is what we're measuring here. It's measured as the amount of solute dissolved at a specific temperature. The units that we use for solubility are grams of solute per 100 grams of solvent. It's always 100 grams, and that's going to be important later. Remember that. So our first vocab word here is a saturated solution. This is a solution that's containing the maximum amount of solute dissolved at a given temperature. Next, we have an unsaturated solution. This is a solution that can still dissolve more solute, so it doesn't contain the maximum amount of solute yet. And then we have a supersaturated solution. This is a solution that's holding more solute than it can theoretically hold at a given temperature. So here's some examples. So in this picture here, we have 30 grams of sodium chloride, and we're adding it to 100 grams of water. When we stir it up or let it sit for long enough, it all dissolves, it goes away. So the resulting solution is unsaturated, okay, because if it was saturated, it wouldn't all dissolve in. If I added 400 grams of salt to 100 grams of water, the resulting solution would be saturated. 36 grams of it would dissolve at room temperature, but there would be 4 grams of solid sodium chloride undissolved on the bottom. No matter how much you stirred this thing up, this 4 grams wouldn't go away. That tells me that the water is holding or dissolving the maximum amount of solute that it can at that temperature. That's why this solution is considered to be saturated. In this next picture here, we have a picture showing saturation and equilibrium. So in picture A here, we have our solute in the bottom of our beaker filled with water, and the arrows represent the dissolving of the solute into the water layer. In picture B here, we can see the water is getting more brown, kind of like the color of the solute, but some of the dissolved solute is recrystallizing back in the solid. That's what the black arrows are representing. However, more is dissolving. We have a larger arrow. These larger red arrows mean more is dissolving than is recrystallizing. So we're still dissolving here, and we're not saturated yet. This water is becoming more concentrated. And when we get to picture C, the arrows are equal, which means the amount of dissolving is equaling to the amount of recrystallizing. And when that happens, we say that the solution is saturated and it is at equilibrium. A supersaturated solution can be formed by a process like this. So if I have 100 grams of solvent or solute, and I'm dissolving it in this solvent here at 25 degrees Celsius, and 5 grams of it dissolve, but 95 grams are still dissolving, the solution at this point is said to be unsaturated. Eventually, 91 grams will dissolve and 9 grams won't. And at that point, it's at reached equilibrium and the solution above is now saturated. Okay, so at 25 degrees Celsius, it can hold 91 grams. But if I heat it up, that's what this little triangle represents. If I heat this solution up to 50, I can dissolve all 100 grams. Now it's unsaturated now at this point because at 50 degrees, it can probably hold more than 100 grams. But if I cool this solution down very slowly, very carefully, back down to 25 grams, and I don't touch or I don't disturb the beaker at all, if I'm lucky, I can still keep all 100 grams dissolved in the solution. Now at 25 degrees Celsius, it's saturated. It can hold normally 91 grams, but I've tricked it by doing this careful slowing down to hold 100 grams. Now the solution is said to be supersaturated. And if a precipitate starts to form, if it comes out of solution, and you can do this a couple of different ways. Sometimes it happens naturally. Sometimes if you add a little crystal, the whole solution will crystallize. At that point, it's now a saturated solution. So here's one more picture just showing the difference. In an unsaturated solution, more solute dissolves. I can keep dissolving solute. In a saturated solution, no more solute dissolves. I can keep adding solute, but it won't dissolve into the solution anymore. In a supersaturated solution, added crystals can grow if you touch or disturb the solution or add a seed crystal to allow the crystallization process to happen. So here's table G. So let me show you how to use table G. It is unfortunate that it is not color-coded. We have lots of different ionic and there's some molecular substances on here, but the lines are all black and white, and so you really need to pay attention and follow where the lines are and which arrow is pointing to which line here. Some other things to know here. If you end up on the line, on the curve, the solution is saturated. If you're below the line, the solution is unsaturated. And if you're above the line, the solution is supersaturated. The units are grams of solute per 100 grams of water, and it says that right on the y-axis here, grams of solute per 100 grams of water. If this value changes in the question, like if all of a sudden they say you have 200 grams of water, or 300 grams of water, or 50 grams of water, your answer needs to be adjusted. I'll show you some example questions and how. So here's our first practice question. According to reference table G, how many grams of sodium nitrate must be dissolved in 100 grams of water at 10 degrees Celsius to produce a saturated solution? So the first thing we need to do is find amongst all these lines where sodium nitrate is, and it's up here. Next, we need to go to the temperature that the question is telling us. We're at 10 degrees Celsius, so I put my finger on 10 degrees Celsius, and then I go up until I reach that sodium nitrate line. And then I read over, and it says 80. So my answer here is 80. At 10 degrees Celsius, a solution of 100 grams of water would be saturated with sodium nitrate when you dissolve 80 grams of sodium nitrate in that water. Here's another one. Based on reference table G, a solution of potassium chlorate that contains 20 grams of solute dissolved in 100 grams of water at 50 degrees Celsius is best described as what? So they're looking for unsaturated, saturated, or supersaturated. So let's see. First I like to go to the temperature, 50 degrees Celsius, and then I read up to the line of the chemical that they're asking, and then I look at where I am compared to this line. So if I went all the way up to the potassium chlorate line, it looks like I can hold a little bit more than 20. And they're saying I'm only at 20. So there's a little hair difference. It's not much, but maybe 2 or 3 grams more I could dissolve to get to that line. So technically I'm underneath this line. That would make this solution unsaturated at those conditions. Next, based on reference table G, what is the maximum number of grams of sodium chloride that will dissolve in 200 grams of water at 90 degrees Celsius to produce a saturated solution? So they've changed our grams of water. You need to pay attention to that. We are at 200, not our normal 100. So that means whatever our answer is, we're going to need to double it. Okay, so first we should figure out the temperature. It says we have, we're looking for sodium chloride. And okay, so this arrow is just reminding us that it's not 200 like the question says. This chart will tell us 100. So again, we should go to sodium chloride, and we should go to 90 degrees Celsius. And we go up till we reach that sodium chloride line, and then over, and it says 40. Now it could hold 40 grams and 100 grams of water, but we're not in 100 grams of water, we're in 200 grams of water. So we need to double our answer to 80 grams. Next, a solution contains 35 grams of potassium nitrate dissolved in 100 grams of water at 40 degrees Celsius. How much more potassium nitrate would have to be added to make it saturated? So we're getting a little bit harder type of question here. So we find our potassium nitrate line, and we find our temperature. 40 grams, we go up to where it says it contains 35 grams. So we stop at 35 grams, which is about halfway there. Okay, but potassium nitrate here would be saturated when it is holding about 64 grams. So the question is, how much more would I have to add to get it to be saturated? So I just need to look at, well, how much more would I need to add to 35 to get to 64? That's about 29 grams. Okay, next, a student uses 200 grams of water at a temperature of 60 degrees Celsius to prepare a saturated solution of potassium chloride. This solution is cooled to 10 degrees Celsius, and the excess potassium chloride precipitates or settles out. The resulting solution is saturated at 10 degrees Celsius. How many grams of potassium chloride precipitated out of the original solution? This is about as hard as these types of questions can get. Let me show you how to tackle a question like this. So again, we need to remind ourselves that we are at 200 grams of water, not our normal 100 grams of water. So we need to look at the chemical we're dealing with, so we need to follow this KCl line. and go to our temperature. It says at 60 degrees Celsius, we have a saturated solution. That would be about 45 grams in 100 grams of water, but we're not in 100 grams of water, we're in 200 grams of water. So we need to double that to 90. Okay, it then says that this solution is cooled to 10 degrees Celsius. So at 60 degrees Celsius, it's holding 90 grams of solute. But if I cool this down to 10, I just need to follow this line backwards to 10 degrees Celsius and then read over. At 10 degrees Celsius, it would be saturated holding 30 if I was at 100 grams of water, but I'm not. I'm at 200 grams of water. So I need to double this 30 to 60. So the question was, how much of this original solution precipitated out? Well, if it held 90 grams at 60 degrees Celsius, and then I cool it down to 10, and it's now only holding 60 grams, what's the difference between those two? 90 minus 60 is 30 grams of KCl precipitates out. So let's wrap things up here. For solids and liquids, as the temperature goes up, the solubility usually goes up as well. For a gas and a liquid, the effect is opposite. Think soda. If you want soda to dissolve better, you need the temperature to go down. As temperature goes up, gas solubility goes down. Think of thermal pollution or soda going flat on a hot summer day to help you to remember this. Also, you should know how to use Table G to answer solubility questions about specific substances. If you need any help with this or you have any questions, please let me know.